You just can't take a bucket of mud, or in the case of Factory Butte behind me here, 400 feet of a mud slurry, and put it into a microwave and turn it into clay and then mudstone in just a few minutes, or even a few weeks, or even a few months. If you can understand that, then you can understand how young age creationist flood geology, it just isn't possible. Yeah, we're talking about the mud problem, and thanks to YouTuber Gutsick Gibbon for popularizing this term and showing how the physics of how mud turns into rock puts flood geology in a vice that's as tight as the famous heat problem that she's also popularized. And here's the kicker. The clearest, most quantitative statement of this problem was published in a creationist journal. It's either a bold move to stimulate future research, or it's a giant self-own by creationists. For me, it's a clear expression of how the flood geology model of young Earth creationism to explain the origins of the geological column is just untenable. So just what is the mud problem? Well, creationist flood models need vast thicknesses of fine-grained sediment called silts and clays. Those have to be deposited quickly and then turned into rock just about as quickly. Clay layers always start out highly saturated. The little tiny grains that make these frameworks are really flimsy. The pores are very, very tiny, especially as it becomes consolidated. And almost all the load that's above it is going to be sitting on top of water rather than the clay grains. For mud to become walkable, just firm enough for you to be able to stand on top of it, much less becoming rock, the pore water pressure, the pore water that's in that original mud slurry, it has to dissipate slowly by draining through all the little tiny pores while the grains squeeze closer and closer and closer together to make this compact clay. That slow squeeze is called consolidation. And it's the consolidation problem that really is the mud problem. Gutsick Gibbon absolutely nails this with this intuitive version of the consolidation or the mud problem. She points out that you can dump mud fast. You can create a lot of mud really, really quickly, but you can't make mud stiff fast. The physics, it just doesn't let you. And her video, The Mud Problem Precludes Young Earth Creationism, it lays out this narrative very clearly. I'm going to stand on her shoulders and on the original author who brought this problem to publication to take you through a bit of the math and the field test that present this as a fatal constraint to young Earth flood geology. So before we turn to a little bit of math, let's put a picture in your mind of the problem we're trying to solve here. Here is Zabriskie Point in Death Valley. We're looking down a side canyon toward above my head. There is the bottom of Death Valley below sea level. And here we have a solid 500 feet of this yellowish mudstone, right? 500 feet of consolidated, very fine particles that originally had to be deposited somehow. And if they were deposited in a global flood, it wouldn't have been a slurry, a giant slurry of mud that all of this had to consolidate, meaning you have to squeeze all the water out between all the particles to be able to make this clay stone, which eventually then lithifies into stone, and then eventually now is eroding before our eyes. It's the consolidation of this material that's the biggest problem for young Earth creationists. It's really very simple physics, and that's what makes this problem so stark for the young Earth creationists, just like the heat problem. Engineers have had a clock for clay consolidation. Well, consolidation of any materials, really, but we're focused on clay. On clay consolidation since the 1920s. It's Terzaghi's consolidation theory. In words, we could say that the time to reach a given fraction of consolidation scales with the square of the drainage length and inversely with the coefficient of consolidation. Yeah. Okay, that probably wasn't terribly helpful. Okay, so let's work our way through this formula in maybe more common language. Engineers use this simple timing rule of thumb, and it's written compactly there in that mathematical formula. And the parts of that formula are this. Well, T is time. That's how long you're going to have to wait for the target amount of consolidation. How much time? That's the question we want to know. How long is it going to take to actually get rid of that much water out of this material? In this case, out of the mud. TV is the time factor itself, saying like we want to get to 50% or 90% or so consolidation. H is the drainage path, right? The drainage path would be the distance water has to travel to escape. Oh, now if you've just laid down 500 feet of mud, sure, the top little bit of water in the very top bit of mud can evaporate, right, from it. And that evaporation will then pull on the water below it and, evaporate more water molecules. But how does the water in the mud 500 feet down get out? It has to work its way up through the pores, eventually being squeezed out on the surface. And so the distance that the water has to travel, so you can easily imagine that the distance the water has to travel, the longer it's probably going to take. It's h squared because typically the water is only going in one direction. The water isn't dissipating downward, especially, and this would be true in a global flood scenario, right? You've just stacked up lots and lots of layers of sediments that are all full. They're all saturated with water, right? And where's the water going to go? The water has to go somewhere before you can lithify it into rock, right? Consolidate all that material and then lithify into rock. The water has to escape, can only go up. So in this case, after Terzaghi's point, at Zabriskie. So at Zabriskie's point, you have, I was saying, 500 feet or so of mudstone. That's at least 500 feet of full thickness. Actually, it would have been a lot more than that originally because it's consolidated. And all the particles have become closer and closer and goes together. So the whole thing has shrunk. Just like, if there's mud outside and the water evaporates from that mud, it consolidates, shrinks, and often forms cracks as a result. And then we've got the coefficient of consolidation, right? That's a combo property. That's a property that measures how fast the clay can relieve the pressure, right? The higher the CV value, the faster the water can escape. Depends on how easily the water moves through the clay, or how permeable it is would be another word to use, and how squishable the clay skeleton is, or how compressible it is. So imagine sand, all right, at the beach. Water washes up on shore, it mixes, or you stand there and you're playing around in the sand, and you notice how quickly the water will move through the sand and out of the sand because the pores are fairly large, and the size of the particles are large, and it's not very compressible. They're all touching each other. You can't compact sand much more than it already is. But that's not the case with mud, right? Mud is mostly water, with lots of little tiny particles, or grains, we would call them. So the basic takeaway here is that if you double the drainage path, the time it takes to squeeze that water out is going to quadruple. Go from a 1 meter clay to a 100 meter shale, and you've just multiplied your waiting time by 10,000 before you even ask it to get to 90% consolidation. This isn't controversial at all. Pick up any geological, geomechanics text or primer, and you're going to find the same relationship and standard values for how long it takes to get to different percentages of consolidation. So most simply, we could say consolidation time equals how fast the water must travel. All right, square that, divide by how well the clay or any material lets that water out. Yeah, these numbers got to hurt if you're trying to consolidate the history of the Earth into 4,000 years. So what counts as, let's say, reasonable for fine-grained, say, marine clays? The type of material that's building up at the bottom of the ocean from fine particles raining down. Typically, hydraulic conductivities, or the rate at which water can move through that particular sediment, are around 10 to the minus 11 meters per second. I'll show a chart later that will give you some perspective on what that number actually means. But it's actually a very slow value in terms of how quickly water could move through that. If you add that pore water movement, that slow rate of pore water movement, to the corresponding consolidation coefficient, how the grains are going to compact over time, they're small enough to make even thick clays painfully slow to stiffen over time. Plug those into Terzaghi's clock and ask for, say, a 50 to a 90% consolidation in layers that are tens to, say, hundreds of meters thick, which we find very frequently in the geological column. And you're going to end up with thousands of years minimum to millions of years, not months and centuries, for consolidation to occur. So not looking so good for the young Earth creationist flood geology model. The physics just says no. Let's just say when you mess with physics, we're going to need to make it hurt. This isn't just me cherry picking. This is the central point of Scott Dunn's paper in the Creation Research Society Quarterly. And I'll talk a little bit more about the significance of this paper being published in a creationist journal in a few moments. He points out that when you use standard published soil mechanic parameters, thick mud deposits demand geological time to dewater and gain strength. Hence the clay consolidation problem and its implications for flood geology models. Hey, engineers love a model. And geologists, they love their cores. And Scott Dunn is all about modeling and testing these ideas and testing these formulas. And Scott Dunn has personal experience with this stuff. Here's his Google Scholar profile, just showing a few of his publications. I think it's enough to see that he has practical, real-world experience with these equations, right? Coastal engineering, liquefaction, consolidation, those would be his specialties. He's used this formula before. He has seen the practical outworkings of how long it takes for mud to consolidate. Now, Scott Dunn in his paper chose to use a particular example, one he was somewhat familiar with, and that's from the Labrador Sea. Specifically, ODP leg 105 hole 646B, and that is a 767 meter drilled hole below the seafloor. Right, and it has very thick mudstone successions from the late Miocene and the Holocene. I'd just like to point out that the Miocene and the Holocene in conventional dating are 30 million years and less, and so are considered by many young Earth creationists to be post-flood deposits. And so this makes it even more challenging because this is something that's happened in their worldview in less than 4,000 years. And yet this 767 meters, or you think of it like 1,500 feet of material has been deposited, and yet it has consolidated and turned into mudstones and other siltstones and rocks, all right, during that time. When he asks, and what he does is he takes this particular drill core and he asks the question, how could we explain the observations that we make from the drill hole? And he asks a really simple, but I think devastating question. What consolidation timeline fits the measured strength and compaction profile that has been observed, as Ken Ham likes to say, this is observational science. He runs 3 different scenarios in his paper. The first is just hyperfast deposition, days and weeks of deposition very, very quickly during the flood, or if you prefer, sometime after the flood, maybe sometime around the Ice Age or something like that. All right. And what he finds is the column stays severely overpressured and therefore is very weak. And of course, lithification can't really take place because the pore water hasn't been able to escape yet. And yet the material is lithified. Now, you might be wondering about the whole overpressured thing. The overpressure thing, if you deposit a lot of material very, very quickly, there isn't enough time for the water to escape through the pores, right? And then you keep piling stuff on top. So you're going to end up with a lot of weight on top. You might think, well, that helps. You got a lot of pressure, and pressure should be able to squeeze the water out. But where does the water have to go? The water has to go up. And yet you're adding more material on top that also has pore space that it has to move through. And so what you end up with is overpressure, too much pressure above, say, a mudstone, which has a significant water content. And therefore, pressing down on that water doesn't actually push the water out. It creates an instability such that if there's heavier, denser material, that material might sink in, sort of pushing aside the mud. Now, what would happen if that actually happened, right? You had that much overpressure, which is going to cause a variety of different break points, all right, in the columns or in the layers of sediment that have been laid down, is you should see a convoluted material, right? You should basically see bubbling up of the mud, right, through the sandstones and other silts that are above it. But this isn't the observation. This isn't a typical observation found in many places in the world. So that doesn't really fit the model. The observation, the observed column, doesn't fit So then you could say, well, maybe we give it a couple centuries, right? Give it some time. We give it a couple hundred years. It's still too fast. You have excessive pressure that continues to persist. You still have too much material on top pressing down. And what it's pressing down on is a column of water, essentially, because there's more water molecules in mud than there are grains of mud material, right? And therefore, the pressure is all on the water. And therefore, there's going to be insufficient strength to hold up the material above it. And again, you're going to have a collapse of the stratigraphic layers. Well, what about the multi-million year deposition, model? Now, this doesn't say that a massive amount of material is deposited really quickly and it's going to take millions of years to dewater it. No, the idea is that you have millions of years to deposit the material. Let's go back to thinking about the ocean. You have a rain of material falling down. And if you were to, step on the bottom of the ocean, just like you step on the bottom of the lake, it's all squishy, right? There's a high water content there. It's very, very soft and you sink into it. But eventually, the farther down you go, you'll realize that it becomes denser and denser and denser. There's less and less water, even at the bottom of a lake where there's lots of water. Well, what's happening there? The grains of material are consolidating and the water is coming up. All right. So as pressure is pushed down, yes, the water is actually squeezed out of the mud farther down below, and it's working its way to the surface. Right. And so as long as you don't have too much material added on top, you can continue to consolidate that material. The formula itself tells us that if you only have a 1 foot thick layer of mud, it really won't take that long to dewater it, right? Because it has access to the surface, right? You don't have to go that far, right? But as you get to more and more and more and more and more, and if it was all full of water, it would take a long time to get rid of that water. But if you have millions of years where you're slowly adding up a few inches at a time, material over a year, the material below is going to gradually be dewatered. You have gravity, and gravity is actually pulling the grains down more than the water molecules themselves. And so you will get consolidation, even at the bottom of the ocean, at the bottom of a lake. So if you just gradually stack up material, you can get layer upon layer upon layer upon layer upon layer of mudstone, fine-grained materials for hundreds and hundreds, if not 1,000 feet thick. But you have to do it gradually over time. In this case, millions of years. So only the slow multi-million year scenario matches the logs and the mechanical expectations. This is a paper that came out in a creationist journal. And it's using standard engineering math to challenge other young earth creationists, saying, if your model insists that muds formed in a global flood year or in a rushed post-flood century, let's say, the physics says, nope, don't work. Here's a table right out of his paper, giving you an idea of just how long it would take just to get to 50% consolidation for different types of soil types and different thicknesses. Just 50% consolidation. This means that the material has the potential to consolidate a lot more than it already is. And in other words, also get rid of more water out of it. So we have fine sand, silt, and so forth. The coefficient of consolidation is how long does it take to consolidate? I don't think it should be a surprise to you that silty sand and fine sand, consolidate very, very quickly. Whereas silt, smaller particles take longer. Clay, calcareous ooze, they take much longer. They're much, much smaller particles. And as a result, because there's so many of them, the pore spaces are such that it's harder to dissipate the water, harder to move the water through that column. So what's the estimated time to reach? And here's where the numbers become really real, right? The estimate to reach 50% consolidation in years, if you had a 10-meter thick layer, fine sand can consolidate in 0.006, of that. All right. So not a tenth, not 100th, 6/1000th of a year. All right. In order to consolidate that. That's not very much time. Creationists can handle that in their model. But if you have clay and you have a 10-meter thick layer, you're looking at 60 years, right, to consolidate that. And that's just to reach 50% consolidation. more than double that to reach 90% consolidation, because the more it consolidates, the slower the water, the slower the escape occurs. So it's not a direct linear relationship. 100 meters thick, right? You've got, think of it, 300 feet of mud laid down. But then suddenly you're at 6,000 years, right? Right there. A global flood mixes up a whole bunch of material, and very quickly, here's a whole bunch of mud laid out, right? 100 meter, 300 feet of mud. That's 6,000 years to consolidate down to just 50% consolidation. And if you get to 1,000 meter thick layer, of which there are 1,000 meter thick layers, not necessarily absolutely pure layers of mudstone or shales. They might be intermixed with a few, layers of some other material, but nonetheless, there's in the geological column way more than, in most places, more than 1,000 meters thick of this type of very fine-grained material. You're looking at 600,000 years to get to 50% consolidation, and you're going to need to get more consolidated in order to turn it to rock, to lithify the material. So this creates yet another problem, right? And Scott Dunn mentions this in the paper. It's called the deposition rate wall. The problem is this: you can only go so far before it fails. It's another problem that's hiding right in plain sight. If you try to stack up fine little tiny grains of sediment on top of each other with water around each one, okay, right? Sure, they're being sort of held in a column by the fact that there's more mud around it, right? But it's very fluid. And as you stack up more and more and more, and the weight increases, the pressure from above increases, right? You're going to outpace the ability to drain that material, right? To get rid of the pore water, right? So you keep jacking up the pore pressure, meaning if you keep adding more material on top, remember there's 20,000 or more feet of sediments in much of the geological column in different places on the earth. If you just keep adding more to the pore pressure, right, that material is going to fail, right? It's going to slide, slip. Whole layers are just going to try to slide away as something heavier sort of tries to go underneath it, right? You got those sands that are consolidated. They're much denser, all right, than the mud is. Eventually the mud will become more dense than the sand, right? And we see layers of mudstone underneath sandstone. How does that happen? Slow deposition of muds that turn into clay that are very dense. Then you can add sand on top of that. You can't take a thick 10 meter section of mud and then add heavy sandstone on top of it and expect you to have nice, flat, even layers of sediment continue through the whole process of lithification. Right? You're going to have mass transport, movement of that material, disruption of that layer of mud. So what Dunn does is he quantifies this physical ceiling, right? This limit to how sustainable deposition rates are for clays. And he places that on the order of 0.1 meters per year. That is 10 centimeters a year. In other words, you can add 10 centimeters of material per year on top of what's already there. And you can add, the next year, you can add another 10 centimeters. Then you can add another 10 centimeters. And although that's going to add up to meters over time, right, you can't add 5 meters at one time without having this failure of the column. Add 10 centimeters, and it has enough time over a year to dewater enough that it becomes consolidated, and then you can add more mud on top of that. It becomes consolidated, you add more on top of that. So your max rate is 10 centimeters, 10 centimeters, 10 centimeters, 10 centimeters under ideal conditions in order to stack up a thick deposition of clay. So go above that, and as I said before, the system just can't stay mechanically stable. Flood models, by contrast, they need rates of deposition that are meters today to 10 meters per day, sustained over large areas. That's not just off by a little, right? That's off by orders of magnitude. And stability physics says it's going to collapse. These are collapses we don't observe in the geological column. at least not on any wide scale, the type of wide scale you would expect with a global flood. Hey, a couple other pictures to visualize what's going on here, and then we'll get into some other consequences of this for flood geology. So I just took this picture. I just want to note there's a little penny down there to give you an idea of size. I took this picture along Route 6 in Nevada. And what this is this is a, all right, this is a metamorphosed claystone. So these grains this is very, very, very hard rock. But the grain size that makes up the original layers is on the clay sort of side of things, right? And what's interesting here is you see layer upon layer upon layer upon layer upon layer of material here, as if it's sort of like either annual rings or maybe several years of deposition, changes in the climate. So you have slightly smaller particles versus slightly larger particles at other times, depending on what's happening in the environment around it. And so you just end up stacking up these layers. You know, when I stood here, and I'm not showing you the rest of the column here, but this is, I estimated about a 40-foot tall road cut, all with these thin layers of what originally would have been mud laid down that then consolidated before new layers were laid on top over time. And so this is right here, just 40 feet, that there's no mechanism in flood geology to just deposit all of this at one time or within a few days or even a few weeks or even a few months, because that stack of 40 feet is not going to hold this pattern, all right, of thin layers, right? The water content of the original material laid down would be too great to handle the pressure of the material above. Yeah, so here I am with two of my sons, and we're hiking Sheep Mountain, which is off to the left here. This is in Wyoming, the Bighorn Basin. And we had started out, you can't see it. My car is actually in this picture. It's way over here, this area, but this is layers upon layers upon layers upon layers of various, mostly sort of mudstone, some siltstones, but eventually what becomes shales. And they're all in various states of erosion here. The shales obviously were deposited, or the original mud or material was deposited in a shallow sea. And so just gradually building up as very, very small raining particles to the bottom of the sea and gradually accumulating. And so the different colors represent different environmental conditions under which this fine rain of particles were consolidating and building up at the bottom of the sea. All right, and then off in the distance over there is a very high ridge. That's about 600, 700 feet high over there. And that's almost all fine-grained material as well. There's bentonite over there. That's what this area is famous for in terms of the production of bentonite. So this is a vast area of fine-grained sediments that are stacked in layers upon layers upon layers. And if you think about the whole area, this is easily at least 2,000 foot thick section of primarily fine-grained mudstones originally, or mud material that had to be dewatered, right? And then lithified, and then later on eroded to what we see today. For flood geologists, when does this dewatering occur? Like actually during the flood? Yes, I said that, material underneath a lake can get dewatered over time. There is a pull, there is action of dewatering and consolidation. And as consolidation occurs, the water is being moved up into the lake itself. But we're talking about, as I said before, we're talking about long periods of time to do that. How does it do that during a flood? And it has to be dewatered in order to become lithified, turned into rock, in order for one to argue that after the flood, as the waters ran off the land, it then scoured this whole area out and it made this, did all this erosion into rock. It's soft rock, but nonetheless, it is lithified material. Where does that fit in the timeline? And so another example that Scott Dunn brings up in his paper is he brings up the very practical question: how do you get the millions and billions of fossil footprints in the fossil record. Young creationists like to say, like, well, maybe animals were struggling in the water, and then there was some area like a mud flat where they walked out over that mud flat and left their steps. Great, there's mud there. And yes, it's soft, and so therefore when you step on it, it makes something like this. Here are some sauropod footprints at the very famous Bolivian Cal Orco paleontological site, where there are tens of thousands of footprints. But the fascinating thing about this particular location is that there's thin layers of basically limestone type material here, which is also a very fine-grained material, rock. And yes, that would have been a very soft material as the dinosaur stepped on it. But then a few inches below, there's another layer, and there are footprints below that. And then there's another layer, and then there's footprints below that. And then there's another layer, and then there's footprints on there. If this would have all laid down very, very quickly, and it was all muddy material, when that sauropod stepped on this, they should have just sunk right in, many, many feet down. The fact that a huge multi-ton sauropod could walk across this muddy surface and have their feet only go down an inch or two tells us what? It tells us that what's below it is already consolidated. Right? How did that get consolidated? Right? It just showed up on the surface and these sauropods are there. How did the layers below consolidate? How did they dewater in the middle of a flood? And it had to dewater multiple times because these are constantly laid down on top of each other. So what I'm saying is the dinosaur feet, they don't lie. There's an observation. Those are observations. And we have many observations of this. And the observation isn't just of, hey, there's a footprint from a dinosaur. It's also, what is the depth of that footprint? What does the material look like in the layer below that footprint? Does it push all the way down through multiple different layers? Dinosaur tracks that are found in fine sediments, they require undrained shear strength, it's called. The water has to have been drained from it. Even that layer on the top has to be thick enough that it left the impression after the dinosaur moved on. In order to be thick enough, it has to have already been somewhat dewatered. And that comes from evaporation, right? The water is evaporating, so that means it had to be exposed to the surface for some period of time. Right? If it wasn't dewatered, at least in the beginning stages of dewatering, it would just slump back the way it was. If your column, the entire column of material that's below it, is rapidly deposited as an undrained slurry, which is what it would be if you're just like you got stuff mixed up in the water column and it's just falling out and being spread out over the land, it's mud. The very existence of extensive, sharply preserved trackways, right, in flood-assigned horizons, it just contradicts the notion that the underlying muds were freshly dumped and still should have been overpressured. The dinosaur should have just collapsed right through that mud, multiple layers down. They should have been stuck in it. See, consolidation time, it's just not optional. It's recorded in the rocks that we see. It's recorded in the rocks that we observe. We can see that they have experienced long periods of time of consolidation. We have abundant evidence that is present that this takes time, right? Again, it goes back to really simple, basic physics. And look, we use these rules and these formulas all the time to make really practical decisions about risks in depositional environments today. And we can see the geological column shows the very same rules have applied throughout time. Again, these are just core principles about how matter interacts with other matter. So let's just get rid of one common dodge that I think creationists will use. Now, many creationist articles, they point to lab flume tests, experiments in the lab in small scale, right? And they say that mud can be deposited under higher flow than once thought. But deposition rate, again, just depositing mud, that's not the same thing as consolidation time, right? Sure, you can deposit a bunch of mud really quickly. And as Gutsick Gibbon would say, you can't make that thick fast, even if you can deposit it fast. Those flume results, which, they might be useful for bed forms and laminations, they don't just magically drain kilometers of pore water through what are nanoscopic pathways. There's no physical way to develop rock-forming strength of waterlogged mud in just months. So let's talk about this paper and its unusual nature, its unusual place where it has been published. Let's give credit. I got to give a lot of credit to this unusual venue. I give credit to the Creationist Journal for publishing it. It really is remarkable, and it's commendable that the Creation Research Science Quarterly was willing to run Dunn's analysis. Their willingness to publish this technically competent internal critique, right? A critique of other young Earth creationists. I think this pushes their conversation forward. I also want to commend Gutsick Gibbon for picking this article up, distilling it for a really wide audience, and pointing out that Scott Dunn is not a young Earth creationist. So again, a young Earth creationist journal allowing a non-young Earth creationist to publish in their journal with a challenge to other young Earth creationists. And all he's doing is he's just doing the math, all right? If you watch Gutsick Gibbon's video, which I'll link below here, she goes into a lot more details on the math if you really want to see some more examples. So how have young Earth creationists responded to this, right? Because it is a challenge to young Earth creationists. It absolutely is. All right. I've done a literature check. I've looked around to see, I've hunted for responses by young Earth creationists. And since this paper's publication, it was originally accepted in 2023, late 2023, but it wasn't published until the winter issue in 2024. I think that winter issue came out probably early fall. So it's been out now for, I would say, about a whole year. Has there been any technical young Earth creationist rebuttals that address his actual claims, his actual examples? I mean, those claims include Terzaghi's scaling, his realistic consolidation ranges of 10 centimeters per year of clay deposition, the ceiling that he puts there, that's just based on physics. And his Labrador Sea borehole fit that fits the expectations. What is observed is exactly what you would predict to see from the millions of years expectation. Okay, so far I've only seen one actual serious engagement with this particular article. And this engagement isn't even trying to provide an answer to Scott Dunn's challenge. It's more like a repackaging of the challenge to other young Earth creationists and an acknowledgement that this is a real question that we need to address. And I say that because this comes from the New Creation blog. And the New Creation blog published this response here. You can see February 14th, 2024. Oh, you know what? I just said that the winter issue from 2024 probably came out in early fall. Apparently it came out a lot earlier than that, because here we have a response to it already earlier in 2024. So this article has been out at least for a year and a half then. And the New Creation blog, as they say, New Creation exists to propagate the real work of creation scientists using the Genesis paradigm to develop testable models. Now, Scott Dunn isn't a creation scientist, but they're acknowledging that he has delivered them a challenge, and that creation scientists, they presumably exist to take real work like this and try to understand it within the Genesis paradigm, or their interpretation of the Genesis paradigm. And so he wrote this article, Christian Ryan wrote this article, Mystery of the Flood Mud Rocks. And he picked out a perfect image for this, because it illustrates just what I was saying before about footsteps stepping onto mud, right? This is a nice illustration of like what the world might have looked like right after the flood, right? As the flood comes to an end, the world's just covered with mud, unconsolidated mud. And Dinosaur stepped into that. They should have just sunk. They wouldn't make footprints. So this is a very apt image representing the problem, the mystery of the flood mud rocks. And I'm not going to go through this whole paper. I'm just going to take you down to the conclusion. Even if the solution to the mystery of the flood rocks does turn out to be of non-natural origin. Now, see, in the paper, they acknowledge, okay, here, they actually outline what Scott Dunn's argument is. And it's like, well, it's just basic physics. And it's an admission that our current model, all right, of trying to explain naturally, through natural mechanisms, how the flood could have deposited the rocks that we see in the geological column. It don't work, all right? It does not fit this problem. This problem is not solved by any known natural mechanism. And therefore, one possibility would be to turn to what? A non-natural origin or non-natural mechanism to explain how the mud got consolidated really quickly and lithified into rock in time to be able to hold up the thousands and thousands of feet of rock that are above that particular mud. And he goes on to say, like, well, excellent examples of how this might be done should be found in other submodels of the flood. One good example is Russell Humphrey's proposal for the removal of excess radiogenic heat during the flood. In other words, we have this heat problem as well. And so other creation scientists have been working on that, and they have found like little bits and pieces of things that might remove some of the heat. Doesn't solve the whole problem, but maybe if we just cobble together a lot of individual separate explanations that all might have been happening, we might come up with something that could explain it. Another example is Dr. Coulson's supernatural formative processes model of the events that unfolded during Creation Week. Yeah, Coulson has sort of a mixed model in which he has supernatural intervention that changes various forces, causing things to occur very, very rapidly, much more rapidly than they could do under any known process today during the Creation Week. So that's a mixture of like some things happen according to the processes we understand, but some things happen to processes that we don't understand. And not only do we not understand them, we think they were actually supernatural and therefore unreplicable today. So the conclusion of his whole description of Scott Dunn's work and the problem that exists, which is recognized in this paper, is, but for the moment at least, the solution to the mystery of the flood rocks eludes us. Right? That so far has been the main response that I've seen. So let's hit quickly on some possible counters. Right? Maybe mud rocks can form ripples in fast water. Right? You do see ripples. If you go to a lake and the lake has moving water, you'll see ripples in the mud. All right. Yeah, well, that's true. I mean, you can get ripples. That's true. And it's kind of interesting. It speaks to how beds are arranged, right? And thinner layers and thicker layers and so forth. But it doesn't tell us how fast thick clay turns into strong compacted rock. All right. Deposition again doesn't equal consolidation. And that third one there, maybe there's some unknown future young Earth creationist physics. That's sort of what Christian Ryan is suggesting might be possible. But if there's some unknown young Earth creationist physics, presumably with some sort of bit of supernaturalism involved in there, then it's not really an empirical flood model, is it? It's just a placeholder for potential miracles. Dunn's point again in this creationist venue is, for a viable flood model to exist, it has to quantify lithification with real equations under real parameters. And if you can't do that, you can't say that the flood geology model explains the geological column. So we're left with some challenges here. This is an open invitation to flood geologists, right? Just go out, pick one thick, fine-grained sequence of rock. Like, say, maybe what's underneath the North Sea or the Gulf of Mexico, which is an absolutely massive stack of mud, which if you drill down into, the farther down you go, the more consolidated it is, and it eventually is rock. And take those and show us a calculation, right? Show us a calculation. Specify H2, the thickness of the formation. Figure out the drainage conditions, right? What's the permeability of that rock? How much could it be compressed? Look at the overpressure ratio. Calculate how much material is on top and how much pressure that would create if the material was still mud below. And that overpressure is really important because if you have too much pressure above and the water can't escape, the rock's not going to consolidate. I shouldn't say the rock. The mud's not going to consolidate. And it's never going to lithify. It would still be mud today, right? Even if it were trapped and unable to escape, right? Because the material above it lithified and then no longer could you pass much water through it. We should find mud underneath thick layers of rock potentially in the young Earth creationist model. All right. You have to reproduce the observed strength and compaction profile you see in the cores that we have evidence of that we can look at. Right. And you got to try to do that without just invoking exotic parameters. Once you do that, exotic parameters would be supernatural mechanisms or just saying that there's other mechanisms that we don't understand today, because the basic physics here is pretty simple and undeniable. So that's the bar that Dunn has set for young Earth creationists. I'd say you got to meet it, or just admit your model needs millions of years just for the mud part of the geological column. So what do we got here? If you could say the heat problem boils flood geology, and the heat problem is a very serious problem, then we could also say that the mud problem probably cements the lid shut. The governing equation is simple, the parameters are measured, and the conclusion is pretty brutal. Thick clay takes geological time to dewater, to strengthen, and to lithify. That's why you just can't microwave a kilometer of clay and turn it into rock. So I really want to thank Scott Dunn for putting hard numbers into this unusual venue. And I want to thank Gutsick Gibbon for making the topic accessible and sparking broader interest, though not nearly as much as it deserves, especially among young Earth creationists. They're the ones that need to be coming to this challenge, and they should be talking about this. And so far, I don't see a lot of chatter about it. It's sort of like, I hope it kind of goes away. If a detailed technical reply exists, hey, link it to me. Seriously, I'd love to take a look at it. Until then, I would say that mud, math, and millions of years stands as a very well accepted, very well supported understanding for this portion of the geological column. So that's my challenge. That's Scott Dunn's challenge. So all I'm going to do now is just show a couple pictures to reinforce a few points. I'm back here at Sheep Mountain, looking across this valley of this massive amount of sediments that have been laid down. And again, the point here is that this is easily explained by millions of years. This whole area covered by a shallow ocean, mountains at one time off in the distance, draining into this shallow sea. And this would have been potentially tens, if not hundreds of miles from any shore. And so the material that comes in, eventually the larger particles get sorted out early, right? Fall out. And you can see that in the geological column as you travel toward areas where we think that the edge of this inland sea was. But as you get out here more toward the middle of the inland sea, all you have are the very smallest particles that end up in solution, and they are just very gradually falling down to the bottom of the sea. This rock here is probably building up on the order of millimeters per year, originally, the material at the bottom of the sea. And at that rate, it easily gets dewatered over time as it stacks up, right? Not going to have any problem of overburden, right? Overpressure, right? As the particles fall, they gradually begin to consolidate, right? They become more and more and more dense over time as the water escapes from those pores. More material falls on top. But the rate at which the material is falling on top is not so high that it's going to create any problems. And so you end up with these massive layers, thousands of feet thick, of very fine-grained material. In the flood geology model, the only way to lay down several thousand feet of fine-grained material would be to do it within the space of a few days, a few weeks, a month at most. And if you're laying down material that fast, it's going to be full of water, right? And you're going to have all the problems we just talked about. Just this scene alone is absolutely devastating, right, to the young Earth creationist flood geology model. Here I am in Nevada. This is the Wheeler Formation. And the Wheeler Formation are these very hard shales that are very, very fine-grained material. Again, this would have been shallow, in this case, shallow sea, offshore sea material. Here's a trilobite. My son and I were there. We were cracking open rocks and finding trilobites. Saw hundreds of trilobites that particular day. And these trilobites living at the bottom of the sea, being covered up by sediments, either as they died, or in some cases, what they had was they did have potentially little avalanches that covered them with several feet of sediment. Now, what I noted is that this material is not like nice thin layers. I mean, they do crack open generally in sort of flattish layers, but some of it's a little bit jumbled up material. So as you look at the wall, here's one of my better plates that we found. Those are about 2 inches in size. These are all Cambrian, right? Relatively early Cambrian rocks, and so very, very old, over 500 million year old rock. And so they have very simple trilobites in them. Again, you can see the way that this cracked is it's not on just a thin plane. This is more like material that is the bottom of the sea, and you had material that's flowing down and then stacking on top. And some of it is kind of wavy and not exactly flat lines. All right. So this wouldn't be like at the bottom of a placid lake. These guys got covered over fairly quickly, but not with like thousands of feet of material, but like, maybe a foot or two at a time. And then above all of this rock is a several thousand foot tall mountains of magma, all right, volcanoes. And those volcanoes don't have any flood sediments on them. So they're like some kind of post-flood sediment. So very interesting location. All of this material is extremely fine-grained material that would have all had to have been laid down by a flood very early on in the flood stage. And then somehow material stacked on top of that while still keeping the nature of this material. So I also mentioned that I would say something. I may have mentioned earlier that I would say something about this particular article. Scott Dunn had contacted me several years ago, and with this particular problem. Right, this particular issue of what he called the mud problem. Well, he didn't call it the mud problem. He called it the consolidation problem. And he said he was thinking about writing something, and I was wondering where, like, he might be able to publish it. And I don't know if I'm the only one, or I can't remember the exact timeline on this, but I had suggested he might want to try to publish it at a younger creationist journal. Write it in the context of being a friendly. A friendly engagement in which respectfully, taking the flood model and doing these comparisons and creating a challenge for young earth creationists. And he took up that challenge and wrote this paper. I saw early drafts of it, and it's a really simple, straightforward paper with simple examples. And I think you see it's a significant challenge to young earth creationism. And if they want to be taken as a serious scientist and as a serious model for the history of the world, then this is something they have to respond to. This is something some young earth creationist has to work on this problem, because it is a problem. It very much undermines flood geology. And so I was really thrilled to see him take up that challenge of submitting to a young earth creationist journal and getting it reviewed, and then actually getting it accepted there. And again, I give huge credit to the editors at the Creation Research Science Quarterly, which is the Creation Research Society, to publish this article. That took a lot. I'm sure they've gotten some grief from other young earth creationists for publishing it there. Because people like myself and Gutsick Gibbon and others will make a lot of hay out of this, because it's a really significant article. I think it's one of the most important articles I've seen written in a young earth creationist journal. All right, let's leave it there. Thanks. The mud problem. Yeah, it's a problem. Thank you so much for listening. Hit like, subscribe if you found this content helpful, and we'll see you on the next one. Bye-bye.